The videos which you are about to see were all written for use in MAE 672 Computational Fluid Dynamics 1, which I taught during the spring semester of 1987. This course was offered live by satellite through the Virginia Cooperative Graduate Engineering Program. MAE 672 is a master's level introduction to the field of computational fluid dynamics, although at least half of these programs could be used in various undergraduate classes. CFD involves the numerical solution of the governing equations of fluid mechanics and is used extensively in the design and analysis of aircraft, turbomachinery, separation equipment, manufacturing and forming processes, and even is used for predicting the weather. All these programs were written in True Basic, which I chose for its excellent graphics capability, as well as for the easy transition from Fortran. The computer in the studio is an AT&T PC6300 with the clock speed reduced by about 30% for compatibility with the broadcast system. This semester, I had students live in the studio here in Charlottesville, at VCU in Richmond, at the Peninsula Graduate Center in Hampton, a couple students at Lynchburg College, at 3 sites in Northern Virginia, and even one student in Pittsburgh. The first problem deals with the solution of an ordinary differential equation using Runge-Kutta integration. The equation is the Blasius equation, which governs the flow in a self-similar boundary layer. In this third-order ordinary differential equation, 2 of the boundary conditions are given at eta equals 0. The third one, unfortunately, is given at eta equals infinity, which we take here to be eta equals 10. Since we don't know the boundary condition on f double prime at 0, we guess it and keep trying until we meet the boundary condition out at infinity, which here is that arrow at the upper right-hand corner of the screen. Now you can see that we've undershot the arrow, and we'll use a half-interval method to improve our guess until we exactly meet it. One of the reasons I got into the computer graphics was that my class was scheduled from 6:30 to 7:45. At that hour, the competition is pretty stiff. There's Tom Brokaw, Dan Rather, and of course,
Wheel of Fortune!
This next one deals with a familiar problem from undergraduate heat transfer. Here we look at a 2-dimensional steady-state conduction problem. The region in this case forms the base of the plot that you're seeing, and the bars that are being plotted are proportional in height to the temperature. The boundary conditions are that along the back boundary, the temperature is held at unity. On the 2 boundaries in the foreground, the temperature is held at 0. And on the left boundary, we keep an adiabatic boundary condition. We're using an iterative technique to solve the equations in this case, something called Gauss-Seidel Iteration. And you can see that we're sweeping our way across the mesh and plotting at each node on this mesh a bar that's proportional in temperature, proportional in height to the temperature of that cell. Out here in the foreground, nothing much happens originally, and so we can come back and look at it in a couple minutes. Now we're in the final sweep, and you can see that the changes are pretty small. The boundary condition over on the left, that it be adiabatic, is nearly satisfied. That is, the temperature gradient there is nearly 0. And you can see that it's almost converged. For a simple rectangular geometry, as we had in the last problem, it's easy to generate a mesh. For more complicated problems, we've got to go to some lengths. In this one, for instance, suppose that we wanted to compute the flow over an idealized 2-dimensional rotunda. To do that, we would map the upside-down U-shaped region from the physical plane on the left into the rectangular computational plane on the right. Then we do our calculations in the rectangular computational plane where the boundary conditions are easier to apply, and we'll map those results back into the physical plane. We can come back when the calculations are done and show you what we have. Now with the calculation done, we can come back and look at the results. It doesn't look like much on the computational plane over on the right-hand part of the screen, but if you look on the left, you see that we have a fairly decent mesh. Now we're ready to do the calculations, which would again be done in the computational plane and then map back to the physical plane. In this one, we look at a one-dimensional transient conduction problem in a geometry that's close to home. I've used the properties of the walls at Monticello. That is, they are 18-inch thick brick, and I've used a boundary condition at the outer surface of the walls that's appropriate for a day in July with the sun shining directly on it. There's a clock over on the right-hand side of the screen to tell you the hour of the day. Here we are in the early morning hours, 4 o'clock, 5 o'clock. Now as the sun rises, you can see the temperature at the outer wall shooting up. In the late afternoon it gets quite high, but you can see the enormous effect of the thermal capacity of these big, thick brick walls. In fact, if you look at the inner boundary now at x equals 1, the inside of the house, you can note that the highest temperatures don't occur until actually the wee hours of the morning. This final demonstration is actually the term project. By being able to show it right in class, I was able to give the students an idea of what they should expect. The problem that we're solving is the problem of Baynard convection in a two-dimensional region. Here we have a fluid layer, and we heat it at the bottom, cool it at the top. The fluid at the bottom heats up, is less dense, wants to rise to the surface where it cools off and falls back down. Looking at the contours of stream function on the left and using the key at the bottom, I can determine that the fluid is flowing in a clockwise direction, and then comparing it with the plot of the isotherms on the right-hand side of the screen, I can see that that flow is bringing the hot fluid up along the left-hand boundary of the region and carrying the cold fluid back down on the right-hand side of the boundary. Well, there you have it. I did meet my goal, which was to have one new demonstration on average for each of the 28 classes. That involved some 3,000 lines of programming. The students each wrote 10 programs as homework. As you can see, the semester has taken its toll on me, and I'm ready to crawl back into my hole until next semester. Thank you.